Good morning, everyone. Welcome to the lecture 7.2 of Power System Stability. In this lecture, we are going to introduce the equal area criterion to investigate the system stability without using solution of swing equation. We know that the swing equation is a differential equation which represents the dynamics of power angle, and if we solve the swing equation, we could get del of t or the time series of del of t or the plot of del of t, which will give the dynamics of the system. But you may need to use numerical methods, iterative numerical methods like Euler method or Euler-Cauchy method or Runge-Kutta method or whatever. So instead of using these methods, we'll use a direct approach called equal area criterion to investigate the system stability without the solution using numerical methods. Now let's start with the swing equation itself. M d squared del by dt squared. This is already derived in a previous lecture. M d squared del by dt squared equals Pm minus Pe, which is the mechanical power minus electrical power, which is the accelerating power Pa. Let it be equation 1. Now from this equation we can write d squared del by dt squared equals Pa divided by M. Pa divided by M. Now in general, if we have the plot of power angle with respect to time, del of t versus t, then if we get like a damping oscillation like this, if there is damping, then we say that the system is stable, right? We know that there is acceleration and deceleration happening after an initiating disturbance in the system. So this acceleration and deceleration, if it finally leads to a new steady state del value where there is no further deviations for del, then we say that the system is stable, right? Then we say that the system is stable. Instead, if it grows like this, if the amplitude is increased or if the amplitude is increasing, then we say that the system is unstable, right? Now, if the system finds by itself a new steady state value where there is no further deviations, then we say that there is no further dynamics for del, that is d del by dt equals 0. D del by dt equals 0. So this can be a condition for stability of the system with respect to power angle. Now we have our equation 2 as d squared del by dt squared equals Pa by M. If we multiply the LHS and RHS of equation 2 by 2 d del by dt, it will become d squared del by dt squared into 2 d del by dt equals 2 Pa by M into d del by dt. Now this can be written as, the LHS of this equation can be written as d by dt of d del by dt the whole squared, right? Because d by dt of d del by dt the whole squared is d squared del by dt squared here into 2 into d del by dt, which is the LHS of this equation. LHS of this equation. Okay. This is equal to, again the same thing, 2 Pa by M into d del by dt, which is equation 3. Now if we integrate equation 3, you will get this integral of d by dt of d del by dt the whole squared will become d del by dt the whole squared only, right? Which is equal to 2 by M is a constant, integral del naught to del Pa d del. We are integrating with respect to del because the dynamic variable is del. This is equation 4. Now At d del, the initiating disturbance happens at d del, which is the initial steady state operating point. From that point, after the disturbance has happened, there is a swing for the power angle. So if it is increase in mechanical input, or initially if the disturbance happens to be like this, to lead to cause a, which causes a positive PA or positive accelerating power, then initially there is an acceleration, then it goes beyond a point, and if there is a deceleration, it comes back. So there is a swing, and this swing is the oscillation. If there is enough damping power in the system, then the oscillation will damp out and it will reach a new steady state operating point. Okay, so this range of del along which the oscillation happens, this is the del naught to del region. Del naught to del region. Okay, see, del is not a value. Okay, del naught is a value. Del is not a value, it's a variable. So del is basically varying from del naught to some point. Okay, that is what is the dynamics of del, d del by dt. Okay, now let's convert del, the power angle, as or let's represent the power angle del as the difference between the physical rotor axis and the synchronously rotating frame. So let's do like this: del equals theta e minus omega s into t. For synchronously rotating frame, we have synchronous speed into time. This is displacement. Okay. Now this is the, because of electrical power increase, or because of the difference, because of the change in difference between electrical and mechanical power, there is a change in theta e, right? So there is a change in difference between the synchronously rotating frame and the relative difference, angular difference between the synchronously rotating frame and the physical rotor axis, which is del, the power angle. Okay, now if this change is not there, if this change becomes constant, we say that d del by dt is 0. D del by dt equals 0, right? So if it finds its own new steady state operating point, then d del by dt will become 0. So here we can take the fourth equation, can be written as equation 4 is d del by dt the whole squared equals 2 by m into integral del naught to del pa d del.